Okay, all welcome as we continue our lesson. At least today is a very good day, stable network. We praise God for that. Okay, so I got some feedback. Yeah, some people have already done the needful and they'll be able to calculate it. Okay, so now why do we have to calculate it? So that whenever we are giving a redox reaction, we can be able to predict. Yes, Aziz, thank you very much. So in the second place, thank you guys. Prince, you guys are fantastic. So you can see in the second place, you can calculate the oxidation state of uh, manganate ion here. That's manganese because oxygen is usually minus two. So by the time I calculate it, some other people have done it already. Please, if you don't understand it, please always state that you don't understand and ask questions. All right, so that is that for it. I hope it's clear to all of us. Now, I have a very interesting website here that you guys can just go online and do more practice. You don't worry, you don't need to struggle. When you get the notes, you can copy the link and visit the website. Okay, thank you guys. All right, so now we are going to the main business of this session. Identifying identify what is changing in the charge, what is oxidized, and what are the oxidizing and reducing agents. So here, based on what we have learned, we can be able to identify the oxidizing agent and reducing agent. Very simple. Calculate the oxidation state. Calculate their oxidation state. Here, bromine is all on its own. That means it's zero. Here, this is aluminum iodide. Aluminum iodide. So we have to calculate the one for aluminum iodide. So we have to calculate the okay here it's but iodine here has already become zero. I'm going to show you the key things that you need to do so that there is no question you'll not be able to know whether it's an oxidizing agent, oxidation reaction, or a reduction reaction. Trust me today, no darling. So bromine here is so look at what happened to iodine. Iodine has changed. Now look at this aluminum. Aluminum is a metal, so we have to calculate it. Aluminum. So we have aluminum is plus 3 Al okay, plus so we have two of them, so the two will always be there. I don't like putting, but because of my critical students, you have three, okay, three iodine. So I put the I in brackets so that you know that it's iodine. So the charge here is equal to zero. All right, so iodine is usually so this is two times aluminum is usually plus three. All right, so uh, plus we don't know the state of iodine there. So that is 2 times iodine. So 2 times 2, that's 6 I. So please take note, is equal to 0. So that means I here, I I here will not be, okay, let me, so I is equal to minus 1. So iodine here is minus 1, while iodine on the right hand side there is 0. So bromine here has also changed to minus 1, so you calculate it for yourself. So let's see. It says what is oxidized and what is reduced. Remember, oxidizing agent is reduced. Take note. Reducing agent is oxidized, so no big deal. So now, which one is reduced? Yeah, which one is reduced? Bromine has gone from 0 to minus 1. That's reduced. Is it reducing, right? Yes. So it has the oxidation states have reduced. Simple, simple. So if they ask you what is oxidized, obviously you just write what is reduced. So you write Br2 is reduced. Reduced, reduced. So it's reduced, and why this whole of this compound is oxidized. So the question is, Which one is the oxidizing agent? So Br2 is reduced, Al(I3) is oxidized. It's as simple as that. That see what I hope you saw how I did it. I just calculated the various oxidation states on the right hand side and on the left hand side. So the one that is lower, so uh, bromine here has gone from 0 to -1. So that means it has reduced. Simple. So which one is my oxidizing agent? Automatically you know that oxidizing agent is reduced. So this one becomes a OA, oxidizing agent, while this one becomes my reducing agent. It's as simple as that. No cramming. Ensure that you do not cram these things. What do you just know that first thing first, calculate the oxidation state. When you have calculated the oxidation state, check the one that has become smaller, that's reduced. Simple. So now that has become reduced is called the oxidizing agent. Automatically, the other one on your reactant side is what becomes the what? Reducing agent. Okay. So how do you now teach yourself? Okay. It's very simple. You can see how I did it here. I only calculated the oxidation states, and when you get this slide, you can also always do it. So, all right. So let's check up another equation. So what is reduced and what are reduced? Atoms in look at this one. I put this. I put something here. Atoms in a polyatomic ion do not change in charge. Now, what do I mean by polyatomic ion? Ions that are more than one. So you treat this as a single. So everything here is a single charge. So you treat it as a single charge. So that's why I call it. This one is -1. Trioxo nitrate. Look at this one. SO4 is usually treated as a single charge. So SO4, you usually call it SO4 2 minus. So SO4 here too is usually is a single charge. So also, what are those polyatomic ions? So let me just type it for you to remember. They have SO4, they have SO3, they have NO3. Okay, you have OH. Okay, so remember all this OH. Okay, you have HCO3. Okay, this one that okay, yeah, something like this. So these are some polyatomic radicals. So they are usually together. They don't change. So atoms in a polyatomic do not change in charge. So that is very very important that you remember all this. Very very. Hope it's clear to you. And so you can use who is going for it. So which one is? Remember, oxidizing agent and reducing agent are usually reactants. They cannot be products. Okay, so magnesium here is on its own, so the oxidation state of here is 0. So if the whole of this SO4 is -2, that means you just say Mg -2 is equal to 0. Okay, very simple. So that means Mg is equal to what? Plus 2. If you carry the 2 to the other side. So I hope this is very, very clear. Very, very clear. So that means magnesium has changed from 0 to 2. It has increased. That means automatically, did it increase? Yes. So that becomes, magnesium becomes my what? Reducing agent. No big deal. Mainly it increases. It becomes your reducing agent. Look at what about this one now? Copper here, the same thing. So Cu -2 is equal to what? 0. So that means Cu is equal to +2. So if it comes over here, Cu is now 0. What happened to it? It has reduced. So that means the whole of this compound here is oxidizing agent. I hope my chemistry is on point for you. You cannot come to this class and you go home the same way. That means you have just wasted your data. But students don't waste data as long as my lesson is concerned. You can do the same thing for BR. You can check out these ones here. Potassium is 0 here, potassium is +1 here, and you'll be happy that you did the right thing. Okay, so no big deal. Okay, so I think this is just the solution. Alright, so redox or not redox. So let's say how do you identify redox reaction? This question came out in WAEC last year and it had about 6 marks. WAEC gave about 4 Yeah, I gave about four equations, and three of the equations are that's three of the equations showed reduction. I think the equation were five of them. Three of them were was redox equation, and two of them were not redox equation. So how do you now know the one that is redox, and how do you now know the one that are not redox? So easy way to spot a redox reaction. Now look for compounds entering and leaving. Look for elements entering and leaving compound. Now this is very very beautiful. You must. This is one easy thing. Look at here now. Hydrogen plus oxygen. What happened to both of them? Both of them are entering. See, that's my English. I told I want to use entering and leaving. So both of them entered. So both of them entered and what formed water. So that means both of them, immediately both of immediately one element is entering, another one is leaving. That means it's a redox reaction. Look at this second one. KClO3. Oxygen has left this compound. Oxygen leaving this compound, that means one of them have left. You see? So oxygen is no longer part of it. That means it's a redox reaction. So let's see how. So look out for their for changes in their charge. So oxygen here, because it's on its own now, is zero. Oxygen here, because it has done what? Because because um it's combined here is minus two. So you can see there's a change in oxidation state. So you can easily do that for hydrogen. So let me show you the synthesis here. Okay, so in the redox, what I have here, hydrogen is zero, blah blah blah. You can see chlorine here is plus five, chlorine here is minus one. Did it increase or did it reduce? It has reduced. So that is different ways you can spot your know if a reaction is redox or not. So let's say another one. Look at this combustion. Yes, combustion, obviously I've already told you that combustion is a redox reaction, yeah, right? So you can check out the oxidation state and even single replacement. Look at this one, single replacement. Single replacement reaction are also redox reactions. So look at what I mean by single replacement. Zinc has replaced copper in the product. Can you see? So that's what we call a single replacement. So whenever there is a single replacement, it's a redox reaction. Sharp, sharp. No big deal. Okay, so look at this combustion here. Hydrogen is plus one here, hydrogen is plus one, so no big deal. Look at here, oxygen here is zero, oxygen here has gone to become minus two. So obviously that's a redox reaction. So single replacement, whenever there is a single replacement, these are what? Redox reactions. Double replacement. I love this reaction. Whenever there is a double replacement, you obviously know that there is no see silver has replaced lithium, lithium has replaced silver, so no redox. So whenever there is a double replacement, it is not a redox reaction. I hope that's very clear. Whenever there's a double replacement, it is not a redox reaction. I hope I'm not. I hope I brought something new to you today, right? Yeah, I trust me. I trust you. Now. Okay, so another one that I forgot to mention here. Most times, it's also double replacement. Is neutralization reaction. You know, reaction between sodium hydroxide and HCl. Let's see what it will now give us sodium chloride and water. So obviously double replacement. I hope you can see here. I can see what I mean by double replacement. So automatically they swapped, and that means this is not a redox reaction. So in WAEC, what WAEC was asking expecting students to do in answering that question was that a lot of students banged was that you cannot just say double replacement or single replacement. You see, when I'm doing my own single replacement, I showed their oxidation states. So you have to also tell WAEC that the oxidation state of chlorine did not change. Is in minus one at the reactant, minus one at the product. Lithium is minus one at is plus one at the reactant, plus one at the product. Nitrate is minus two, nitrate is minus two. Silver is plus one, silver is two. So for every equation that student attended last week, what happens is that most of the time a student will say the oxidation state of chlorine is minus one on the reactant side, and the oxidation state of chlorine is minus one on the product. Let me repeat myself. Oxidation state of chlorine is -1 on the reactant. Oxidation state of chlorine is -1 on the product. So therefore, it is not a redox reaction. That is an incomplete explanation. You must talk about the oxidation state of everything in the compound. Every element in the compound, you must state it before you can score. That was what happened last year. So a lot of students missed that question because they did not simplify for every other species in the reaction. So please, you guys are lucky to be here today. So please don't go home with the same knowledge that you have today. Okay, so you have to be very, very explicit. So redox reactions are composed of usually two half equations, or two half reactions. We call them half reaction. I think I have um, one of the slides that puts the definition there. So half reaction is a reaction that shows only oxidation reaction or only reduction reaction. Okay, so no big deal. So half reactions usually show the elements being oxidized or the element being reduced and the change in charge So I don't understand double replacement. Okay, thank you. Before I go back to the yes, now look at what I mean by double replacement now. Let me go to this arrow. Now look at silver. Silver was married to NO3, but now silver has replaced lithium here. It's now married to what? Chlorine. While lithium was married to chlorine here, now lithium has replaced silver and is now married to NO3. So both of them have replaced each other. So that's called double replacement. So whenever there's a double replacement, such reactions are not redox reaction. Okay, so it's very important. I wanted to show you another. Look at this combustion reaction. But this combustion reaction is not a double replacement because here oxygen was on its own. So because it was on its own, it is not double replacement. Look at single replacement. Zinc was on its own, it is not a double replacement. So that's why it's a redox reaction. So but whenever there is a double replacement, the participating atoms replace each other, then the oxidation stage remains the same. So such reactions are not usually redox reactions. Okay. So let's go back to half equations. So half equations usually show electrons being gained and electrons being lost. All right, so no big deal about that. So we're almost there. Now let's see how to write half equation for this. So I like this is very simple and straightforward. So take sodium. Look at what happened here. That's why we did calculating oxidation state before. So sodium oxidation state of sodium is 0 here. Oxidation state of sodium here has increased to +1. What did I say whenever there is plus? I told you whenever it is plus, that means electrons have been lost. So when electrons have been lost, you throw the electron to the right hand side. So note, E lost electrons on the right side of the arrow. Take note. If electron is lost, it's usually on the right side of the arrow. If electron is gained, usually on the left side of the arrow. So no big deal. So fluorine is 0 and it's now -1. So it's now having an extra electron. So it is this fluorine. Take note, it is this fluorine that has gained. So that's why you have to add the electron to it. Take note, you can see here, that's why I'm adding electron to it. It is this sodium that has lost electron. So throw electron away from it. Simple English. Sodium has lost electron. So throw away electron from it. So that's why you throw the electron on the right hand side. So whenever electron is lost, so throw the electron to the right hand side. Whenever electron is gained, give the electron to the person that is gaining the electron. Okay, that's quite easy to understand. So if you write it, so like sodium here, it has lost an electron, where is +1. But these two indicates that there are two sodium. So you multiply through by 2. So that's exactly what happened there. This a single fluorine gains 1 electron, but we have two fluorine here. So that's why you have to put 2 electron. So I hope that's very, very clear for you to understand. All right. Okay. I like this. Interesting. Look at this. I say oxidation half equation always have tails of electron, like electron on the right hand side. Yeah, you leave your electron behind. All right, so let's say I think I've taken this equation here. Let's look at this reaction. So the same thing. So zinc has changed to plus 2. So 0 to plus 2, it has lost 2. You put the electron on the right hand side. Copper, check out the oxidation state of copper here. Copper is plus 2 here. Copper is 0 here, it has lost. But this chlorine here, check out chlorine. Chlorine is no longer in the equation. Why? Why did I remove chlorine? Because it goes to the stadium and keeps watching football without participating in football playing. So it's called a spectator. So whenever an ion does not have change in oxidation state, we describe such ion as a spectator ion. So you do not include it in your ionic. See what I wrote to? You do not include it in your ionic equation. What do I mean by ionic equation? Equation that are showing changes in oxidation states, changes in or showing the various ions in the element. So because this chlorine, the ion did not change, so we throw it away. It's a spectator. Okay, so there's somebody going to the football field stadium to watch and did not do anything. He did not play naira bet. He did not support anybody. Just goes there. Just joking. I'm joking. All right, so these are other half equations. You can see here, remember I told you compound ion, sulfate here, SO4 is minus 2. Remember I told you is a compound ion, so it's minus 2 here, it did not change. It's also minus 2 here, it did not change. So remember I'm talking about SO4, so no change. uh So you can see it did not change, so it's a spectator. Look at potassium here. Potassium here is plus 1. Potassium here is also plus 1. It did not change. It's spectator. So that's why when I'm writing the ionic equation, I did not include both potassium and sulfate because they are spectator ions. So when you are doing your own study, please calculate the oxidation state. So this SO2, SO4 is minus 2. So times 3. So that's you can see here. So that's everything minus 2 times 3 give you minus 6. So you should be able to calculate it. And I know you guys are smart, wonderful students of mine. If you have any problem at the end of this topic, kindly send me a private chat and I'll see what I can do to help you at the end. All right, so that is how I was able to write out these half equations for this chemical reaction. Oh, 101. Time is not my best friend today. So I can show you here split when you are studying your own, learn how to split these equations into half equation. So you can see sulfur changing to sulfide. So this one is now 0, but this one is carrying minus 2. So that means is it increasing or decreasing? It's increasing. So that if it's increasing, that means there is a loss of electron. So put the electron on the right hand side. Chlorine here is 0, but chlorine here is negative. And so please, what did you say about simplifying the equation? Oh God. Okay. I said okay, so how you simplify. So see sulfur goes from here to here. So this sulfur is not carrying any charge and it's alone. So it's carrying a 0 charge. But this sulfur is carrying a charge. So it goes S2 minus goes to become S. So the oxidation state of this one is minus 2. The oxidation state of this one is 0. So that means it has increased. And whenever there is an increase, that means it's oxidation, that's loss of electron. So you put the electron on the right hand side. And what is the difference between 0 and 2? That's 2. So that's why I put 2 here. So that's what the oxidation half of that first equation. But what about chlorine here is 0. So Cl2 change it's not carrying any charge, but this one is carrying any charge. The Cl minus. So that means it has gained electron. So you put the electron on the left hand side. So you gain electron. So how many chlorine is involved? 2. So that's why you have to put 2 here and you put 2 here. So automatically you have gotten your oxidation half. This is your oxidation half. Half, and the other one is a reduction half. Right? So no big deal. Same thing you can do the one for copper. Copper goes from here 0 to plus 2. That means it's increasing. That's oxidation. While silver goes from plus 1 to 0, that means it's reducing. That's reduction. Simple as that. Okay. That's very. I have a very simple way of helping you balance redox equation. Just give me 108. I should be done 108, 5 minutes. I'm sorry, I just have to. So now, very, very simple. Like when I say the simplest step you've ever seen in balancing redox equation is what I'm going to teach you today. Now, balancing redox equation must be one, balance for mass, then balance for charge. Remember I talked about balance for mass and balance for charge. So let's see the steps that you need to do. So ha ha ha. Okay, now the very simple. This is just my very simple steps. Now find the oxidation numbers and use brackets to connect elements changing in charge. Now, so next thing you need to do, balance the atoms by change balance atoms changing in charge. So those ones that are having, remember that I told you, those ones that are having changes in their charge are the ones that we focus our attention on. And look at the next thing I said. If necessary, let's find the electron involved in each charge. Okay, no problem. If necessary, balance the electron by multiplication. Balance all the atoms except hydrogen and what? Oxygen. So what do you do? Balance oxygen by adding water to the side deficient. So if there is a side that have, maybe you have oxygen on the left hand side now, and you now have oxygen on the, you don't have oxygen on the right hand side. So all what you need to do is to add water to the right hand side. Yeah, if you have hydrogen on the right hand side and you don't have hydrogen on the left hand side, so that side that is hydrogen deficient, you balance it by adding hydrogen to that other side, so that you now check for the balance of the respective atoms. I can't lie to you, this is very, this is like the simplest sentence I've shown. Okay, this is another, you see the same thing that I've just talked about. Let me show you this simple equation. Look at this simple equation. It's very simple here. Look at iron, manganese, iron, blah blah blah. So you can see here that this one is very simple. There's, I'm not informed this question. I don't like. I was expecting something more difficult. So you can, so iron is plus 2 here. Iron is plus 3. Automatically, what happens to it? It is increasing. So that means that iron has undergone what? Oxidation. So you have plus 2 here. So if you go to this other side, it now becomes iron what? Plus 3. So when it's plus 3, that means it has increased. So that's oxidation, loss of electron. Now, what about the manganese here? So manganese, MnO4, the whole charge, let me decline this to be looking, I'll be looking around. The whole charge, MnO4, is carrying a minus sign. So remember one of the examples we calculated, but it has changed to what? Mn2 plus. So the oxidation state is has changed to plus 2 on the right hand side. So that means you need to calculate what this are. I've already done this. We got this as minus plus 7 here. So that means it has decreased. See, all the way from plus 7, now it's plus 2. It has decreased. So when there's that decrease, you add electron. So what is the difference in that decrement? 5. So that's why I put 5 here. Then you now add, so there's oxygen here. That means you should add water. Can you remember what I told you? You decide that oxygen is deficient. There's no oxygen on the right hand side, so you add water here. Very simple. There's hydrogen here on the right hand side there, but there's no hydrogen on the left hand side there. What did they say we should add? H plus. So life is as simple as that. Don't allow anybody to ever tell you that oxidation and reduction is the hardest thing. So you have done the simple chemistry. Ladies and gentlemen, you have balanced the charge. All what you need to do is to balance the atom. How many oxygen do I have here? 4. How many oxygen do I have here? 1. So what do I do? Put 4 here. Simple. So that means 4 times 1, 4. How many hydrogen do I have here? 8. 4 times 2 is 8. How many do I have here? 1. Just put your small 8 here. And you are on your way to smiling like Michael Jackson. But unfortunately, we have 5 electrons here. We have only 1 electron here. Yeah. Remember that they said she balanced it. Remember that rule that they said, if necessary, by multiplication. Where is it? If necessary, balance electron by multiplication. So that's why I'm going to come here and I'm going to multiply. So instead of putting 5 here, they said balance it by multiplying. So you multiply the whole of the equation here by 5. So when you multiply the whole of the equation here, this guy becomes 5, this guy becomes 5, this guy becomes 5. Without much ado, check out the next line for your total answer to it. Okay, so this is exactly what I did. Very, very simple. And you are happy. See? So can't be afraid of any redox equation. There are so many examples I put here. You can try this, and I've solved it also. You can now go ahead and read for your own test for oxidizing agent and test for reducing agent. The question here is, what do I need all this redox reaction for? This is 2020. I don't even know if they will do like this, but obviously God will give them wisdom. So 2020, they can ask you state the application of redox equation. You can see here, I've gone ahead to show you where we apply it in corrosion of metals. Metals get oxidized by forming metal oxide. Prevention using oil, use a paint or oil plating or attach negative terminal. Gold doesn't rust. Why does gold doesn't rust? Because it's solely unreactive. So in photography also involves oxidation and reduction of silver atoms and silver ions. So that's the application. Bleaching, like one of the questions I asked you, bleaching of chlorine by addition of oxygen, that's oxidation. I remember that thing I told you the other day. Some people were contesting the answer, but I know my chemistry very well, so that's the correct thing. So you have to add oxygen, that's oxidation. Okay, explosives also form neutral nitrogen from ionic nitrogen compounds containing different nitrogen ions. Okay, so reactivity of metals. Metals that are highly reactive can easily undergo oxidation, while metals are moderate for those with low reactivity undergo reduction. And ladies and gentlemen, this is where the cookie crumbles. I want to believe that I've done my best to bring down this topic. Okay, so for those of you, like I said, asking for physics lesson, it's not really free and it's not easy to get lesson teachers to do free lessons. But I will do my best to get teachers. If they cannot do it free, that means you have to pay. It's not compulsory. So, sir, send sir the link. What link? Is it the link to the WhatsApp or link to the question I put earlier? If it is to the WhatsApp, you have to join so I can get these notes. So when you get the notes, the link is in the notes. If I'm right. All right. So
For the question,
teach us stoichiometry. But you know he come on David, what happened to you yesterday? Were you not in the class last Saturday? We did stoichiometry. Uh, we were there with Oh, tell me about the YouTube channel. I sincerely apologize. I think I'm becoming lazy. I actually have one of the guys working on the YouTube channel, and the guy it doesn't take anything to create a YouTube channel. So, and the guy was busy editing all the videos throughout the week. So, because we want to send the videos batch by batch, so uh, we have like the first series that will be coming up will be organic chemistry series. So after organic chemistry series, then we now have all of the other topics. So it should come up by Monday, hopefully. I think the guy should be able to do it. I'll send the okay, sir. Send the PDF to I'll send the PDF to you. You can check the WhatsApp. I've already sent the PDF and PowerPoint on the WhatsApp. So, ladies and gentlemen, thank you very much for uh, allowing us to take your time and your Saturday. I hope it was worth it and you have already reminded yourself on how to work on oxidation and reduction. For me, this is the simplest note I've ever used to teach oxidation and reduction. So, have a last weekend and God bless you guys. Bye.